Welcome to this first part of my video playlist about the best methods to convert aliphatic alcohols into alkyl iodides. This presentation is about the use of hydrogen iodide as deoxyiodinating reagent. Hydrogen iodide is the least expensive and most environmentally friendly reagent for converting alcohols into iodides because the only byproduct of this reaction is water. Deoxyiodination is one further possibility to convert alcohols into powerful alkylating reagents. However, as shown in this table, alkyl iodides are only about 2 times more reactive toward common nucleophiles than bromides, but twice as expensive. Alkyl iodides are also less stable than alkyl bromides, and for many synthetic uses, bromides will probably be a better choice than iodides. The mechanism consists in protonation of the hydroxyl group and displacement of water by iodide. Depending on the type of alcohol and solvent chosen, the substitution will be bimolecular or monomolecular. Typical side reactions include the formation of ethers or olefins, but also the reduction of alcohols or olefins to alkanes. Iodide and hydrogen iodide are good reducing agents, capable of reducing a large number of functional groups. Hydrogen iodide can be bought as a 57% solution in water. This is usually prepared by reduction of elemental iodine, for instance with hydrogen sulfide, hydrazine, phosphorus, tetraline or hydrogen. Many examples have been reported of the deoxyiodination of alcohols with hydrogen iodide generated in the reaction mixture by mixing an alkali iodide with a non-oxidizing acid, for example phosphoric acid. Theoretically, phosphoric acid with a pKa of 2.2 is not acidic enough to protonate iodide, but the small amounts of hydrogen iodide produced react quickly with the starting alcohol and are thereby constantly removed from the equilibrium. The acid may also just activate the alcohol by protonation and thereby bring about the substitution without stoichiometric formation of hydrogen iodide. Unfortunately, because of the reducing power of iodide and hydrogen iodide, the scope of these deoxyiodinations is narrow, and the progress of these reactions should be monitored to avoid reduction or rearrangement of the product. Because hydrogen iodide is a very strong acid, these reactions can proceed with inversion, but can also yield mixtures of stereoisomers. The main advantages of hydrogen iodide as deoxyiodinating reagent are its low cost if compared to other deoxyiodinating reagents, and the fact that water is the only byproduct of this reaction. These few upsides, however, are outweighed by several disadvantages. For one, hydrogen iodide is a very strong acid and readily converts alcohols, olefins, ethers and other organic compounds into carbocations, which tend to rearrange and give mixtures of products. Hydrogen iodide is also a powerful reducing agent capable of reducing a large number of functional groups if used in excess and when allowed to react for too long. Then, because of its high price, hydrogen iodide cannot be used in a large excess, and one must take care not to lose it by evaporation. In this example, isotopically enriched C13 methanol was converted into methyl iodide by treatment with aqueous hydrogen iodide. Because in this instance the alcohol was expensive and no reduction to methane occurred, an excess of hydrogen iodide was used. Otherwise, the reaction would have been run with an excess of methanol to provide for a complete conversion of hydrogen iodide. In this older example, again an excess of hydrogen iodide was used, now to prevent an incomplete deoxyiodination, which could give rise to an iodoalcohol difficult to remove from the product. Here, hydrogen iodide was generated from potassium iodide and phosphoric acid, and a good yield of the diiodide was obtained. Cyclohexanol has a particularly high tendency to undergo elimination under acidic conditions. Nevertheless, treatment with sodium iodide and methane sulfonic acid gave mainly the expected cyclohexyl iodide. In the examples on this slide, the goal was to reduce the alcohols to the corresponding alkanes in a biphasic reaction mixture. Elemental phosphorus was added to reduce any iodine formed in order to maintain a high concentration of hydrogen iodide throughout the reaction. Anyway, in these two instances, the reaction stopped at the iodide stage and did not proceed further. This indicates that the adamantyl cation is too stable and not electrophilic enough to be reduced by hydrogen iodide, and that primary carbocations were not formed under these relatively mild reaction conditions. So, what can go wrong? Because of its relatively high nucleophilicity, iodide adds readily to olefins and alkynes. Therefore, if the starting alcohol contains double or triple bonds, hydrogen iodide addition products should be expected. In this example, cyclohexyl iodide was obtained in excellent yield from cyclohexene and in excess of anhydrous hydrogen iodide. This here is an example of the addition of hydrogen iodide to an electron-deficient alkyne. Interestingly, iodide often adds to propiolic acid derivatives to yield cis products. In this example, however, copper catalysis caused the kinetically favored cis product to equilibrate to the thermodynamically more stable trans-iodoacrylate. Hydrogen iodide can also be used to cleave ethers, as shown on this slide. Even the mixture of potassium iodide with phosphoric acid, which is much less acidic than pure hydrogen iodide, can bring about the cleavage of THF and its conversion into diiodobutane, as shown here. A large number of other functional groups will also undergo acid-mediated transformations upon treatment with hydrogen iodide, in particular with pure hydrogen iodide. Further potential side reactions include the typical reactions of carbocations, such as isomerization by hydride migration and Wagner-Meerwein allylic or propargylic rearrangements. Other leaving groups than hydroxyl groups can also be displaced, for instance other halides, sulfonates, alkoxides or carboxylates. If free hydrogen iodide is formed, this is often oxidized by air to iodine, which can then cause the oxidative iodination of various electron-rich functional groups. Many functional groups will also be reduced by iodide or hydrogen iodide, such as benzylic or secondary alcohols, halides, ethers or esters. Even some ketones and olefins can be reduced to alkanes. Sulfoxides are readily reduced to thioethers and haloketones to the corresponding halogen-free ketones. Here are some more examples. Most of them involve mixtures of an acid with sodium iodide, and it should be kept in mind that in none of them hydrogen iodide is generated stoichiometrically, but only in small quantities, if at all. Thus, these reactions will show a different selectivity and byproduct profile than reactions conducted with pure hydrogen iodide. The next video is about the use of phosphorus iodides as deoxyiodinating reagents. These enable the conversion of alcohols into iodides under much milder conditions than those described above and are therefore much more versatile. So, don't miss it.